Okay, so additional topics regarding classification, I think some of those are very kind of important, so we need to go through them. So earlier we mentioned, so when decision tree is naturally a multi-class classification classifier. Naive Bayesian is a multi-class classification classifier. Um, um, the naive Bayesian belief network can also classify two or more classes at the same time. What we learned so far is support vector machine is an algorithm that actually does binary classification. So as we can see from our previous discussion that the work, the entire learning process of support vector machines is to find the hyperplane that could separate data points in the feature space. So it was designed to do that, to separate two classes. Therefore, it's called binary class classifier. But we can certainly make use of support vector machines for a multi-class classification problem. One way we can do this is what is known as one versus all, where we will learn when we use, for example, support vector machines for multi-class classification, we will train multiple support vector machines. In this one versus all method, we will train one classifier for each class. When we train that classifier, we will use the positive class for that class as positive. All the rest, all the examples from all other classes as negative. Then when we use these classifiers, we will a lot of times those classifiers will give a prediction that actually can be used directly as the class label. But other times, two classes could predict conflict class for one example. In those cases, we will need the algorithm to produce some confidence scores, like probability, to help to solve the conflict. Method 2 is known as all versus all or one versus one. I have no idea why all versus all. One versus one definitely makes sense to me. In this case, you will learn many binary classifiers pairwise. So if you have M classes, you're going to construct this number, M times M minus 1 divided by 2 binary classifiers, meaning for each pair of classes, you will create a binary classifier. So this classifier is trained using the tuples of the two classes. That's easily doable. To classify a tuple, then those classifiers going to vote. Then X is assigned to the class with the majority votes. I think in our R exercise on police shooting data, you can see that multiple, it's the support vector machine in E104071 package use one versus one. So you can see this plays out in our R code. Comparison, one versus one seems to provide more accurate result. Performance may be better. However, because you constrain your training example to those classes, smaller training examples, the resulting classifier may be sensitive to the training examples that you used it on. So since we're talking about multi-class performance classification, I think I want to mention And also because in my R exercises, I often just used the accuracy in my get score method. I don't want it to be misleading. It was just convenient to use one score to illustrate the overall performance. If you have multi-class performance classification problem, it is very often that we would report position recall scores on every class. So in this slides, I illustrate once you have the confusion matrix, how you're going to compute position and recall for your different classes. I figure that my practice using accuracy has an impact on students because in student final project presentation in the past couple of semesters, I did not see students use position recall measures in their work. Vast majority of them used accuracy, so I want to draw your attention. When appropriate, you want to use position recall to report your performance. Do we have questions so far? Okay.